Hello friends, today we'll see the microprocessor based temperature control. Of course, the PID controller is used, but the controller used is microprocessor based. Normally 8085 microcontroller is used. In the close-up we'll see the microcontroller, the microprocessor setup over here. And here friends, as you can see, there is one bar. Now this I am going to call it as a process bar. Now what do I mean by process bar? While studying your heat transfers, friends, you must have studied about the thermal storage, right? Thermal storage system, so to say. Now this bar, it stores the heat. Now how it is representative of a process, so to say. Just if you take the example of a room, let us say this room has 10 occupants inside this room, and then it is having air, and we have got so many heating elements. So depending on the heat ejected by each of the persons or the heating elements and the specific heat of the medium, I can tell you how much will be the heat content available in this room, isn't it? So it is the mass of the content, then your specific heat and the temperature change, isn't it? So that will be the heat stored within this room. This is how I talk about the heat content in this room. Similarly, this bar, how much will be the heat stored? How much is the heat stored in this bar? If I ask you a question, how can you compute mass of this bar? Similar to the room calculation that we did, mass of the bar, specific heat of this material, right? And then the temperature change that you are bringing in, isn't it? So that will be the heat contained in this bar. So in this setup, the developers of this setup, they have intelligently used this bar as a representative of a process, right? So here we have a bar which is heated by light. Okay, once the setup is put on, this light will start glowing, and because of that heat, radiation heat, of course, this bar will get heated up. Then you have a sensor which will sense the temperature of this bar, and that sensor will send a signal to this controller, friends. And then actually the fan will be there which will be generating the disturbance. When the air flows over this bar, friends, the heat will be dissipated and the temperature of this bar will change, right? And that will be sensed by this sensor. Now coming to my PID control, in the last experiment also we have seen what is the PID mode, proportional mode plus integral mode plus derivative mode. And as you can see, friends, this is your microprocessor 8085 input device of the keyboard, and this is the display. This is the actual temperature it will be displayed here, and the set temperature is displayed here. And by using these knobs, I can just set the values by using those mnemonic codes of this microprocessor, which I have given in my lab manual. Okay, so I can use it in test mode, I can use it in normal mode, I can measure the outputs. Here in this case the temperatures can be measured directly, and the set values can be adjusted here, range 0 degree, 100 degree, and when the RTD as a sensor is used, I can use those inputs, and then whatever is the output that I am getting from that bar will be taken from that RTD. I can place it here, just plug it here, and that signal will be sent here, and I can measure that signal as well. And friends, as we studied the speed control of a DC motor, the temperature control in proportional mode, temperature control in integral mode, temperature control in P plus I mode, temperature control in P plus D mode, and temperature control in P plus I plus D mode can be studied. And if you remember, the problem with proportional controller was it generates offset in the output. What do I mean by that? Suppose the bar temperature is set for 100 degrees Celsius, right? And then what happens is initially the temperature of 100 degrees Celsius is nicely maintained by this control, by this proportional controller. But let us say what I do is suddenly I blow cold air over this bar. Suddenly I make the load change. Sudden changes in the load if I make, what what happens? My set point originally was 100 degrees Celsius, and that 100 degrees Celsius was maintained by this controller. If I bring about sudden change in the load, suddenly cold air I am blowing, what will happen? The temperature of this bar will be suddenly affected. So, because of this sudden load change, what we had said, the proportional controller has a tendency of generating an offset. What do you mean by this offset? My original set point was 100 degrees Celsius. Because of this sudden load change, what the proportional controller has a tendency, it will just shift its set point to 120 degrees Celsius on its own. So what happens is, my original set point was 100 degrees Celsius. Now the change set point is 120 degrees Celsius. This 20 degree is the offset of this proportional controller. Why the proportional controller is behaving like that? Because it is subjected to sudden load change. It responds to sudden load change by adjusting its own set point, which is not desirable. Because even after removal of sudden load change, that set point will remain shifted. That is not desirable, isn't it? Whatever temperature I want to maintain, that should be maintained. The set point should not be changed on its own. So that offset phenomena can be studied by using this microprocessor based temperature controller, friends. And then how that offset can be reduced or removed by inserting I type of control action inside. If I use P plus I control action, whatever offset just now we discussed, offset of 20 degrees Celsius, that can be removed by using P plus I type of controller. And then by using P plus I plus D controller, we can evaluate the performance curves, and we can conclude that PID controller is the best controller for any process application. That can be proven by conducting experiments for different values of input temperature, for different types of inputs, for step input, for ramp input, for sinusoidal input. How this PID controller is responding can be tabulated and can be shown that your PID controller provides the excellent transient response as well as steady state response. And microprocessor based PID control action provides me more flexibility in my control action. This is how I can conduct experiment on microprocessor based temperature control. Thank you.